Now, a brief discussion on why Maychem's formula works. So some of you might have a question in your mind. If you recall how we derived Maychem's formula, so if we go back to the basic formula, recall K is equal to the present value of the redemption value. So in our case over here, I'm just going to change this up into something like this. So C to the V to the n, that's just K. And if we break this up, and then we dump this C on the inside, we have C minus C to the V to the power of n. Once again, this is K, so you get the usual formula that we're familiar with. So in that problem that we just did, we also have a tax term over here. I'm just gonna disregard that for the time being. So as you see that the way we derive this, we assume that in this case the redemption value, there's only one redemption value. It's not the case of the serial bond that we saw just now. So recall that the serial bond, it has a lot of redemption values. It keeps paying off the nominal value bit by bit. So the amount of coupons that we pay keep on decreasing, and that situation does not correspond to this formula over here. And if we derive Maychem's formula using this formula over here, then why were we justified in using this formula? So why did this formula actually give us the correct answer? So the way I like to think about this is, using the example that we just had, I like to think of it as a combination of 20 bonds. So recall just now we had a 200,000 nominal value, and then at the start of time 5 we keep on receiving this redemption value. So in addition to this, we're also receiving coupons, so the costs that we pay for borrowing money from people. But I'm just going to disregard that for now. We're just going to consider the redemption value. So all the way up to time 24, we keep paying this redemption value, and then it keeps decreasing this nominal amount that we owe. And the way I view this as a combination of 20 bonds, so in that case, the price of the bond is equal to the sum of all these 20 bonds. This first bond over here, this is the bond that corresponds to this redemption value. So there is a bond that has a redemption value of 10,000 ending at time 5. And there's a second one that ends at time 6. There's a third one that keeps on going, and the last one ends at time 24. So if you break this up into 20 different bonds that mature at 20 different times at time 5, at time 6, and time 24, all the way up to time 24, we're essentially just applying this formula 24 times. So for each one of these individual smaller bonds here, if we break this up into 20 different components, each one of these, we're just dealing with the normal situation here. It's not a serial bond anymore. So we're justified in using either of these formulas. But the thing about Maychem's formula is that once I add up all these components together, I will still get this formula. I won't get this formula because the coupon will keep on decreasing if I combine all these. But if I combine everything, if I use a Maychem formula and combine all these 20 prices, I will still get this formula, and I'll show you right here how you can obtain that. So the price of the first bond, I'm going to use Maychem's formula. So K is 10,000 V to the power of 5, and you have your corresponding G and your I, and you have your redemption value of 10,000, so I'm not going to write this out, just 10,000, and then another K, 10,000 to V to the power of 5. So this is the price of the first bond. This is the one that matures at time 5. And then you have a second one that matures at time 6. So you have the same thing. Again, this C is 10,000. And you have the same thing, you go all the way up to time 20. So for the one that matures at time 20 to 24, the V, it goes, you essentially have the same expression, but it goes from V to the power of 24. So if you add these terms up together, if you group up this term, you get V to the power of 5 plus V to the power of 6, all the way to V to the power of 24. And if you'll check this term over here, this is essentially equal to V to the power of 4 times 820, which is exactly what we used to calculate K in the previous, in the example that we just did. So we were completely justified in, at least in using Maychem's formula for that part. But if you observe the other parts, you add up all the C's, you have 20 of these, each one of these is 10,000, you add up to 200,000, and again, you group up these terms over here, you get something that's similar to this part, which is also equal to 10,000 times v to the power 4, 820. So if you see that this corresponds exactly to the c that we use, this is the k that we use. And if you write this out, this is just precisely equal to k g minus g over I c minus k. So for the case of serial bonds, if you break this up into 20 different bonds and you add them up, you'll still get back this formula. So that is why, although we derive Macon's formula using the basic formula, in the case of serial bonds, we can still use Macon's formula to get our answer the way we just did in the tutorial question. So this is why it works, because we can think of it as a combination of 20 bonds. We apply Macon's formula 20 times, and it turns out if you add them together, you still retain this expression. So I think this is the most the most important and most difficult concept to wrap your head around in this course. So I think this is particularly important, and this tutorial question, it's best if you try to fully learn what exactly a serial bond means through this question.